All right, good. We're live. Cool. All right. Hopefully everyone's doing well. Um, Questions. We're in the end game here, and I know other classes are probably still going at a crazy pace. So, we're going to keep talking about some new stuff this week. But no more programming assignments, no ODPs. Can anybody else hear me? Okay, cool. So yeah, no assignments coming up this week. Really, nothing required until the final exam on Wednesday. So your final is a week from Wednesday, 11 o'clock to 12:50, and we'll talk about details of that on Friday. I'd like to mostly spend this week on questions that you have, but barring that, I want to continue talking about processes. I want to look at doing two-way communication with pipes today, and also look at the last weird command we need to talk about, which is dupe and dupe2. And then tomorrow, come back and dig into awk and make sure that we've gone over using awk to do file processing. And then Thursday, probably spend playing around with regular expressions, which we've talked about and you used in homework 8, but we haven't really done a whole lot of exercise with them. So I posted some practice problems a while ago on Canvas, and maybe we'll take some time Thursday to work on those in a group setting. And then Friday we'll just kind of do a quick run through of the whole course and any final comments I can make on the exam itself. We'll talk about then. But any questions before we jump into all of this? All right. Let's take a really quick look though. So we talked a little bit yesterday about this question of how do you calculate trig functions, and I thought it would be fun to just kind of like pull up some code for that. So I did. So here's a sample trig package from IBM. That's part of what's happening when you run a trig function. And I'm certainly not going to go through this in details, and frankly a lot of this is over my head. There's a lot of minutia, but engineering 250, right? We talk about IEEE 754 floating point standard. So that's that 32 or 64-bit pattern that has an exponent, a mantissa, a sign bit, and then all these special cases for representing 0, plus and minus infinity, things like that. So this code conforms to that standard because when you have a floating point number in C, it's coded in binary using IEEE 754. And there's a few include files in there, but a couple of interesting things to point out. This function called polynomial2. So this is a macro, right? A macro is part of the preprocessor. You can define a macro, and whenever you say polynomial2, it gets replaced by all of this stuff. And it gets replaced before any compilation takes place. And this is a macro with an argument, and so if you say polynomial2 parentheses, j, then each of these xx's gets replaced by a j. and this chunk of code will appear in your program and then get compiled along with everything else. And this is doing that polynomial evaluation we talked about yesterday, right? Take some constant, multiply by, x, add your next constant, multiply by x, add your next constant, multiply by x, add your next constant, multiply by x, and then take all of that, and then add your last constant. And then down here, an abbreviated Taylor series for calculating a sine. So, x minus x cubed over 3 plus x to the 5th over 5 factorial, 7th, 9th, 5 terms of the Taylor series. And then a little error correction term that pops in at the end here. And that's really the guts of it, right? So there's, like I said, tons of special cases. And some lookup tables, and some things like that. And this is sines and cosines, right? They kind of go together. But this is just plain old C code. It's confusing if you don't know, what it's supposed to be doing. But it's basically, just calculating a Taylor series. But with lots of edge cases. And I love this, an ultimate sine routine. I mean, that's good commenting, right? And it just decides what to do based on the range of the value that you've given it, right? So depending on the size of the number that you're computing the sine of, right? And these are, IEEE 754 representations of 32-bit floats. And they correspond to, these kinds of ranges for the actual numbers. And it does different things based on that. And then it's got the matching cosine routine, and there you go. So, you can find this stuff for everything that we do in C and everything that we do in Linux. The source code is out there, it's open. And that can be a fun way to, look at different types of code, get some new ideas on implementing algorithms, things like that. All right, so let's go back to playing with pipes, and let me go into a work area. And let me use this as just kind of some boilerplate stuff here. So this was the code we were playing with yesterday, right? Which basically, created a child process and then ran one of two functions depending on whether the process was the parent or the child. And the parent basically, identified itself as the parent, wrote some bytes into this pipe, and then exited, and the child read from the pipe, and then printed what it read to standard out. And that was a sort of basic demo of the idea of sending information through a pipe. So we're going to do something similar today, but we want to establish two-way communication. We want to be able to send to a child process, but also read information back from it. And this is a particular instance of what we can call a client-server model. And client-server is everywhere. Okay, it's really how things interact today in a computer system or across multiple computer systems. So client server. So what's our most commonly encountered example? Client might be PuTTY or SSH, and the server might be SSHD, this SSH daemon, this process that's running on the Linux machine waiting for connection requests. And when you say PuTTY linuxengrcs.com or SSH linuxengrcs.com, you're talking to this program which is called a server. And it says, hey, who are you? What's your password? Okay, you're good. I'll let you in. Creates a bash session for you, and then hands over communication between this client and that bash session, right? Another example would be, whatever your favorite browser is, Chrome, Firefox, etc. That's a client. And what does that client talk to? It talks to a web server. So if you fire up Chrome and you do a Google request, right, you're talking to a web server, a program running on one of Google's machines, waiting for requests from clients. So it listens on what we call a port or a socket. It's port 8080 usually. And you send requests over there, and the server sends back information, web pages, right? We could have, if we had a shared printer among multiple machines, we might use a print command. And over here we have a print server. And when you say print, you don't usually just start shoving bytes out to the actual physical printer. You send those bytes to a program, which is called a print server. And the print server says, printer's in use right now, tell me what you want to print and I'll get to it when I can. Or, the printer's free and the print server sends your bytes out to the physical printer. So this is a really common model in most systems today, client-server. And so we're going to implement a simple client-server model using this idea of pipes and forking a child process and so on. So here's our setup. We're going to start with our main process, just as we did yesterday. And we're going to create a pipe which we can use to send information to a child process. So this is going to run like this. But we're also going to create a second pipe. And the second pipe is going to let us read information from the child. And we're going to create these pipes before we make our call to fork. And since the new process that's created is an exact clone of the original, except for the return from the fork call, this new process will also have its own copy of these two pipes. And they're the actual same pipes. It's not like we take all this stuff and we make a copy of it and give it to the new process. The pipes that we access in this new process will be these pipes that we'll also be accessing from the original main process. All right, so probably the trickiest part of this is keeping your doing your bookkeeping, right? Keeping track of what's what, because we're creating both ends of a bidirectional communication process, and it's really easy to get twisted up and forget like who's sending what to whom, where and how and when. And this is fun when you get it nailed out just exactly right. So I'm going to document what I'm doing on here, and I'm going to keep referring back to this. So I'm going to try to make this, as meaningful. So I'm going to have two pipes. I'm going to name my pipes to child and from child. Okay, and my mindset is, this is going to be my parent, and this is going to be the child process. But I can also think of the parent as being, a client, and the child as being a server. That's not super important for what we're doing right now, but I'm putting it in there just to keep in mind. And my goal for this program is I want a server process that I can send a string to, and the server will convert my string to lowercase. All right, so I'm going to send a string to this child process. The child will convert it to lowercase and send it back to me. Right? Why am I doing this? It's just an exercise. Because certainly the parent can convert the string to lowercase just as well as the child could, but we're creating a server process, right? And anytime I send it a string, it'll convert it to lowercase, send it back to me. All right, and we're going to set this up totally by hand. All right, we're going to write all the code to do this, and we're going to establish the two-way communication. All right, so things to keep straight. When we have a pipeline, that's created with the pipe command, there's a pair of integers stored in a 2-element array that are associated with this pipe. In particular, the n that you write into, that's element 1 of your array, and the n that you read from, that file descriptor, is element 0 of your array. Alright, and this is going to be important to keep track of. So let's write some code. And I did, almost the same exercise in the earlier section, so the code for that is already posted up on Canvas. So you don't need to, be writing this down. So I'm going to hold off on prototyping these functions, and let's a demo of two-way communication between a parent, which is the client, and the server, which is the child. I'll use parallel structure here. Alright, so we need a pair of pipes, okay? Because these pipes are unidirectional. You always write into this end, you read from that end. So I can have, a pipe that I'm using to send from the parent to the child. I can't get anything from the child on that pipe. And I can't let the child start writing into this end, even though the parent can read from this end. I'm not going to know, where those messages are coming from or who they're intended to. So I'm going to use a pair of pipes, one for each direction. Alright, so, I lost my camera. Oh well. I'm still here. Alright, so there's the two integer arrays that are going to hold our ends of the pipeline for us. And we have to actually make these pipes. So I'm going to say pipe, and I'm going to pass to child, and do pipe from child. So we create the two pipes. General note, you should be checking the return status from system calls. When I call pipe, I pass it a 2-element integer array. It will fill in those 2 elements with file descriptors that get me to the 2 ends of this conduit. But this returns a value. It'll return 0 if it's exceeded. But if something goes wrong, it could return an error code. Usually this is going to work, but if we run out of resources, if we've got too many things running, if we've got a runaway loop that's just allocating space for more and more pipes, the pipe call could fail. I'm not going to check any of this stuff. I'm going to assume everything is working fine, but in general, if you were doing this in a system programming course, for example, you'd want to check the return value from all of these system calls. We're going to go on faith and suppose that this works perfectly. So I create my pair of pipes, and now I'm going to create the child process, and so I call fork. If fork returns a 0, I am now the child, so I'm just going to call child, and I'm going to pass both of these pairs of integer arrays, so to child and from child. Otherwise, parent, I'm going to do the same thing. Call the parent and pass the to child and the from child, and so let me prototype my functions while I'm thinking of it. All right. So what does the parent do? So read a string from the user, send to child, read from child, print what you read, and do that all forever. Right, this is just test code. So the arguments to my parent function are toChild, and from child. All right, so let's have a temporary character array. We'll prompt the user. We'll read up to 120 characters from the user and save what they typed in this character array. And then let's go ahead and send the string to the child. So we're going to use a write statement, and we want to write to write into the toChild. So let me make some notation here. So parent should write into, well, we always write into element 1 of our pipe, but we're writing into the toChild pipe. So we should write to toChild bracket 1, and we should read from child, and we always read from element 0. Okay, the child process, well, it's got to write into the from child, right? And it's writing into element 1, so this is going to write into from child bracket 1, and it's going to read from the toChild pipe, and it's going to read from element 0. All right. So this is let me annotate these with write and read. And we could draw an interesting picture of this, right? We basically have, you know, a pipeline connecting these, and we have a pipeline connecting these. So when the parent writes into toChild bracket 1, the child can read from toChild bracket 0. And when the child writes into from child bracket 1, the parent will be able to read that at from child bracket 0. All right. This is the place where things are most likely to go wrong in writing this code. But we'll proceed confidently. All right. So where does the parent write? The parent writes into toChild bracket 1. So write to toChild bracket 1. And I named these things, you know, toChild, from child, to indicate the sense in which these things are you know, delivering information. So parent should be writing to the child. And what we're going to write is whatever the user typed in, which is buffer. And how many characters should we write? Well, you know, we can do string length of buffer and see how many characters there are, but that does not include the null terminator. And since I'm going to read this set of characters on the child side, it would be easier for me if I also read that null terminator, so I don't have to add it on myself. Because there's nothing inherent about sending information through a pipe that says your strings need to be null terminated. Right? I can just send whatever characters I want. They can be binary, they can be, you know, printable characters, whatever. So I'm going to actually send out string length of buffer plus 1 characters through this pipe, which will also pick up the null terminator at the end. And then let's read what the child sends back to us. So I'm going to save the amount read in this variable called amount read equals read. So the parent should be reading from the from child pipe. And we always read from element 0. So we read from child 0, load it into that buffer, and we can read up to 120 characters. And if I believe that the child is sending a null terminated string, I don't really need to use this amount read, right? I can just say printf received from child, and let's just print it out with a %s. And then I'll prompt the user again at the bottom. Alright, and there's my parent process. Alright, so rehashing, right? I'm going to prompt the user, I'm going to enter a loop where I get a line of input from the user. I write it to the child by going into, element 1 of the toChild pipe. And then I read from element 0 of the from child pipe. And I print out what I read back. Now the setup is the child is going to be listening on this pipe. It's going to read in a string of characters, change it to lowercase, and then send it back out through the pipe. So I'm using this totally separate process, right, which is the child process, as a server. I want to convert something to lowercase, I send it to the server, it sends back the lowercase version. Alright, so let's set up a child process. Alright, just read from a pipe, do the conversion, send it back. Alright, so how am I calling this? I think it's to and from. Alright, so that's our pair of pipes. Here's my temporary buffer. And so first thing I'm going to do is read from the parent. So the child process is going to read from toChild bracket 0. So I'm going to read from toChild bracket 0 into buffer. I'll read up to 120 characters. And result will tell me how many characters I actually read. And then I'm going to go through and I'm going to convert my characters to lowercase. Alright, so I'm using something here called toLower. It's a function, it's actually a macro, that takes a character, returns a lowercase version of it. There's a library, C-type, that has all kinds of useful functions for manipulating things character by character, for examining things character by character. And this is really the correct way to do things like case conversion, or checking to see if a character is a digit, or seeing if it's punctuation. The right way to do it is not by looking at ASCII codes, but by using these functions that are prototyped in C-type. So toUpper and toLower are two useful conversion functions. What does it do? Yeah, toUpper really just subtracts 32. toLower really just adds 32 if your ASCII code is, between 65 and 97. But you never want to put that kind of magic number business inside a program because it's fragile, right? If you send this to a machine that doesn't use the same ASCII coding for characters, your code suddenly breaks. And somebody has to go in and figure out what this ASCII code was that you were using back in 2020 and rewrite your code, right? So if you want to convert to lowercase, just call toLower. And this will, work for whatever version of, character representation is being used on this system. And if you try to convert something that's not an uppercase letter, it just returns, whatever you fed into it. So if C is an uppercase, 2 lower returns its lowercase equivalent um, if it exists. Otherwise, it just returns C. And there's all these other is functions, is alpha, numeric is alpha, is digit, is lower, is upper, and so on. They're also in ctype.h. And they return an integer you can use as a Boolean. So you can say, you know, if is digit, parentheses, character, and if that's true, you know, the character is a digit. So we're going to use these. So I'll pull in ctype. And now I can say, you know, go through each character in my my buffer and convert it to lowercase. And then let's write that back to the parent. So this is just a write statement. So the child, last time we have to look at this, child writes into from child bracket 1. So we're going to write into from child bracket 1. We'll write our buffer of converted characters. And how many characters do we want to write out? 1 plus the length of buffer, but I'm just going to use result, right? Because our string's not changing in size. So I'll just write result characters. And again, we should check, you know, error status from these calls and so on. But there's a child process, all right? Now, as this is set up right now, it's not looping. So let's go ahead and put a loop in here. So we'll read from the parent. And if you look at the instructions on read under the return value, it returns the number of bytes you read, but if you hit end of file, it returns 0. So when the parent exits, it will close its end of the pipe, and presumably when I try to read from the pipe, I'll get an end of file indication, and read should return a 0. So I'm going to do my first read up here, and then I'm going to say while result is not equal to 0. So here's my main loop. And then at the bottom of the loop, I'll just do another read. All right, so that's a pretty standard input loop. All right. Do our initial read in the beginning. If it's not end of file, go ahead and convert it into lowercase, write it back to the parent, and then do another read. And go back up and keep doing this. Once our result is 0, we've hit end of file, we'll just go ahead and exit. Alright, this may work pretty well. We'll see. Not too bad. I'm doing string length, so I need string. Shockingly good. Alright, let's go ahead and run this. So enter a string to convert, and let's watch what's happening over here. Right. I have 2 processes E4 running right now. Right. My shell is 17047. That created my process 24997. That's what happened when I said E4. 24997 created another process, 24998, which is also running E4. This first line, this is the parent process, that's the client. The second line, that's the child. All right, so I'm going to say, you know, this is a test, and I get back the lowercase version. This is a test. All right, so I've got a client-server model running. It's on Canvas in the usual shared code area. There's a link you can follow. It takes you to the Linux server. All right, so I've got these two E4s running. Now if I control D over here, which means fgets will return null, which will cause my parent to exit, if everything works correctly, right, my child should have also exited, but it did not, right? And you can see my child process is still running here, but the parent process is one. It's been adopted by a NIT. Because its parent died, it got orphaned. And this will hang out here, you know, until something happens, like I kill it or I reboot my system. So I'm just going to kill it right now because I don't want stray processes running around. Right, so that takes care of that. So why is this process kicking around? Well, because I have ends of this pipeline that are still open. Okay, so here's something that we probably want to do. We know that the parent is writing into toChild1 and it's reading from child0. The parent is never going to use fromChild1 or toChild0. So let's close those out in the parent so that the system doesn't think those resources are in use. So let's go into the parent class. And let's just close the pieces that we don't need. From child bracket 1 and to child bracket 0. And in the child class, let's close out the ends that the child doesn't need. And the child is using from child 1 and to child 0, so it does not need from child 0 and it does not need to child 1. So let's go back in here and let's do our PS. There's our two E4s running. There's our conversion to lowercase. Let's have the parent exit and let's do another PS, and both processes shut down normally. All right, so this is wild and quirky and confusing and all that kind of stuff, right? It's an example of something that is really useful, right? If you want to have multiple processes but be able to communicate between them, right? You do something like this, you know, this is how you can exploit parallelism if you have multiple cores and you want to split your processing into, you know, more than one task. You can set things up like this. Now this is easier in other systems, other languages, and so on. But you know, if you're on a Unix-like system at the lowest level, something like this is what's happening when processes are being created and they're talking to one another. All right, so I'm not gonna throw this code at you on an exam or ask you to you know, write code like this or analyze code like this or anything along those lines. It's really just a first perusal of these ideas. The last thing I want to talk about is this question of, you know, this is all great if we have a main program that's creating a clone and now, you know, both of these processes are, you know, versions of this original main program. But what if we want to work with a different program, right, that's not, you know, a version of this? We will be working with this more in spring when we're doing Java. We'll be playing around with some multiprocessing and we'll be doing networking. So we'll come back to these ideas, but we'll be doing it in a much more comfortable framework, which is Java, and you know, in the swaddling blanket of objects. So it won't look like this, but you'll encounter this in other courses, usually at a university. All right, so we may want to, for example, at some point, do an exec and start, you know, running some new program like our basic calculator, BC, but still be able to communicate with it from this main thread. So here's the cool thing. When you do an exec, right, we've said that we change the essence of this process to now be executing the code from this file. But these file descriptors that we've created, these pipe ends, persist throughout that morphing process, right? So there's one more really cool function which is called dupe2. And dupe takes an existing file descriptor, makes a new copy of it, but then assigns it this number. All right. Now we have our standard input and output file descriptors. 0 is standard in, 1 is standard out. And we have these weird file descriptors, you know, like FD bracket 0, which might be, you know, one end of a pipe that I'm reading from. Here's what I can do. If I say the following, if I say dupe2 FD bracket 0, comma 0, what the system will do is it will make a copy of this file descriptor, which is, you know, this receiving end of a pipe, but that copy will be assigned a file descriptor number of 0. Well, 0 is the fixed descriptor number for standard in. So once I've made this call, anytime I try to read from standard in, I'm going to read from FD0, which means I'm going to read from this pipe. So by using this call, I can change standard in so that instead of reading from, say, a keyboard, you know, or a redirected file, it'll read from a pipe. And so I'm not going to put this code together here. I'm just going to show you some code. So this looks exactly like what we were just doing a few moments ago in structure. It's a main program. There's a pair of pipes. I create a pair of pipes. I do a fork. If fork returns a 0, I call a child process with a to/from pair. Otherwise, I'm just going to execute the parent code right here. So the parent reads from standard in, right, which is just my keyboard, sends what it reads to the child by using a write, reads back a response from the child using a read, adds a null terminator, because I'm not going to assume the child sends me, you know, a bunch of characters followed by a null. And then I'm just going to print out what I got back from the child, and I'm going to do that in a loop. So this is basically the client software that we already wrote. The child software is far simpler. Okay, so I close the unused ends of the pipe that I don't need, and then I make a pair of calls to dupe2. So to child bracket in is this end of the pipe. It's the thing that the child is going to read from. And I take that and I say, let's set that file descriptor number to be this symbol standard in file no, which is just a symbol for 0. All right, so I do a dupe2 and set that input end of the pipe to be file descriptor 0. So now when I read from file descriptor 0, which is standard in, I'm reading from this receiving side of the pipeline. And then I do another dupe2, which says, let's take standard out, which is file descriptor 1, and make that equal to the end of the pipeline that I write into, right? From child bracket out, that's this end right here. So once I do that, anytime that my process, my child process reads from standard in, it's reading from here. And anytime it writes a standard out, it's writing into here, which means it's reading from, you know, what the parent wrote, and it's writing to whatever the parent's going to read. So this is a true server model now, right? And then the last thing I do is I execute this execl command, which turns this process into the basic calculator. All right, so if we compile this, and we'll get tons of errors here because there are warnings. And let's go ahead and run /bc, and let's do a grep. Right. So let's do it like this. So here's the BC that I just ran from the command line. here is user bin BC. This was the child process, but it did an execl, which changed it into, you know, the basic calculator program. But, you know, this is the original ID 241. 241 is the parent of BC, which is 242. And whatever I type in here in my main C program will get sent through that pipe, and BC is going to read it as if it came in from standard in. It's going to perform my calculation and then send the result to standard out, which is connected to the pipe that my main program is reading from. And so my main program receives the answer. And this is more than it might seem to be, right? I can run BC over here and say, you know, what's 2 to the 20th, and it tells me. But what's happening over here is I have a C program, and that C program is putting this into a string, and it's getting back this in a string, right? And if I wanted to do repeated calculations, right, I could take this answer, I could modify it, I could send that back out to the server, the child, read the result back, and do something with that. So it's really, you know, a server process that's running now that's doing calculations for us. So yeah, in 215 we talked about breaking up larger tasks by having friends do the smaller tasks for us through recursion. Because this be done even faster by creating another process. So actually, process creation is really expensive. It's a lot of overhead, it takes a lot of time, and it's limited as to how many processes you can create. You could do recursion through processes, but I would say that's almost never done unless you're trying to take down a system. And if you try to do recursion through processes and you make a mistake, there's a good chance you'll crash your system. So it's a fairly sketchy thing to get just right. But there's no performance advantage. It would actually be a lot worse performance. But that does raise some interesting possibilities, thinking about recursion in terms of process creation. All right, so we are out of time here. I posted code from the previous section that you can find through Canvas, and I made some comments on some applications of this, including if you check out my Minecraft channel, my Minecraft playlist on my channel. I've got some videos where I'm using this client-server model to basically communicate with the server and just force commands into a Minecraft server and use that to do some interesting building and analysis. So that's an example of this. Anyway, that's all I got for today. Have a great afternoon. I will see you tomorrow. Thank you.